closely linked to the memory and cognitive problem. So to develop a useful and multifunctional neural chip is very important. So let's welcome his presentation.
Okay, thank you. Good morning, all. This section, I would like to present another 40 Hertz project. If you remember last semester, I presented a topic about 40 Hertz. But very glad that in the past 1 year, we have seen more and more research in this field. So today's topic is more progressive. We not only stimulate, we also detect the response. Okay, so let's see. Okay, the paper is from Nature Communications. It's a new paper on June this year. Okay, so we can see the relationship between hippocampus, dopamine, and Alzheimer disease. In the photo, you can see the normal brain and the AD brain are very different. By visualization, you can see the difference. The key point is in the CA1 area in hippocampus. So in recent research, people found that 40 Hertz is a good way to achieve Alzheimer disease therapy. There are many ways. For example, this picture is from my last year's presentation. It's a speed up the CF in and interstitial fluid out from the brain. So make the circle, the fluid circle, speed up, then degrade the plaque deposition. Okay, so that's one achievement for in this field. So the rationale is in recent research, 40 Hertz stimulation have been explored as an effective way. In my appendix 1, I have listed many papers, but not complete. You can see there are many researchers in this field. And the way of 40 Hertz stimulation, and not only in electronic ways, but also in optical ways or acoustic ways, by continuous triggering or by only some flickering, all works. So it's a urgent case that if we can get the information, we can know the inner activities inside of our human body or mice brain or human brain. What was really happening during the stimulation, that will be very helpful for our for the research and even apply the research to future therapeutic ways. So the paper, the first thing or the main target is to develop a tool to achieve the bidirectional probing. It means so-called bidirection means it can send stimulation into the brain and also detect the instantaneous response from the brain. Okay, let's see this sketch map. In the left plot, it's a conventional way. If you want to get stimulation and detection simultaneously, there are several probes needed. Okay, so it's not easy in real case because the brain is so small and you need to put many surgical activities. But if you have a device like in the right plot, you combine all the signal together, and stimulation and the response together, then it will be easier to achieve that. So that's newly developed. Similar concept, but they combine the same device. So the paper's hypothesis is first, they hope to know the neural hypersynchronicity firing can be observed. So synchronicity means endocrine secretion, especially dopamine, and the firing. Firing means there are some electromagnetic wave or electrical signal will emit from a human or mice brain. Okay, so that's a more deeper hypothesis is a human body or mice body or even a living being keeps sending out electromagnetic waves. Okay, maybe that's more expensive, but it's a deeper hypothesis. The first thing the researcher hope to see the hypersynchronicity, means the correlation of the dopamine, the secretion and the firing. And the second thing is want to prove that the behavior of cognition can be improved. That's actually a therapeutic way of healing Alzheimer. The third thing they want to prove that in Alzheimer disease treatment can really be seen. You can see the efficacy by some immuno ways. And all the things together, the paper want to prove that this device is workable and successfully achieve the goal. Yeah, so we can say that in the hypothesis 1, 2, 3, if they are okay, they are established, then the fourth hypothesis will also be correct. So they built a device like this. You can see the shape, the outlook, and see the size. It's a very tiny one, like a needle head. But within this tiny needle head, there are still many holes. Actually, there are like some via hole punched through the electronic circuits on it, and even magnified. There's a very sophisticated structure, so many lines go through these holes. Okay, I have written the criterion for this device. I will not go through it, but imagine if you want to develop a device in this case, by this scenario, you need to consider many things, from its material, its electronic, its chemical characters. So actually, it's not easy. It's many things need to be considered. The first thing is you need to keep this signal constantly. Okay, I should remind you, if you have been briefing my present material, you may see many electronics and material processing things in the beginning pages. But don't worry if you cannot fully catch it. Later I will explain in a easier way. Okay, so this will keep the signal constantly stable and keep the signal wave, the waveform, keep it stable, no deformation. And this is a simulation, means this diagram is done by computer, so-called computational electromagnetics. So this black circle may be emulate the mice head. Okay, so this simulation are trying to minimize the electronic field. To minimize it is also try to prevent from more interference. If the field is too large, they will include more interference, and the signal cannot be focused on the certain points. So they must do some simulation, and this simulation by certain geometry, means the pearl head, although it's tiny, but in the tiny area, there are still some geometry design. So they make it minimize. Okay, this page shows there are many layers. Okay, it's called the thin film process. Yeah, more advanced is like a semiconductor, but the thin film is between semiconductor and normal PCB. So once the device prototype was established, they need to do some so-called characterization. The name, the surface processing technologies are so long, but don't worry, you can easily understand it. PTMP means platinum nanoparticles. So it's stable and expensive. So they really pay a lot of investment on it. And this one is carbon nanotubes for stimulation. And they have tested several processes and compare them. And they choose this high one, PTN, this one for stimulation, and the lower one for detection. All these are materials, PDOT and PPY, are materials, some certain materials. And the PPY is flexible, so maybe it's easier for attached to the brain tissues. Okay, by an intuitive one, by seeing the SEM photos, this is the very standard photo for carbon tube, narrow carbon tube. But this one looks like a sponge. So this one is more flexible. So it's chosen to be one of the probe. Okay, so this is the impedance. Please be noted that this scale is different. The left one scale is different from the middle and the right one, and the only middle and the right one can be used because there is one hysteresis. I mean, means closed loop needed. Okay, this one is the IV curve. But maybe if you can remember the fundamental electronics, IV should be some constant, but in this case, in real case, they need to be a closed loop. Then once the voltage is added, in some certain case, the voltage will not increase, but the current will increase. Okay, so this is the left plot, shows the sensitivity. Please see left figure. The red line shows a higher slope. In this case, it means the sensitivity of the voltage to current has a higher sensitivity, means it responds in a more large scale, in a dramatic way. Okay. Okay, so the structure of the research, we can see that's quite a wide scope. The mice is put in a cage, like a Faraday cage. It's isolated, electronically isolated from the outer environment, and the mice brain were implanted by the probe. The probe has a specific name. It's called the neural revive flagship. Later you will see this name frequently, and be connected to the two machines. The machines are big ones. The upper one is for electrophysiology. The lower one is for electrochemical. The output of the two machines are, the lower one is the dopamine's concentration. This is what we want, and there may be a breakthrough in this experiment. And for the upper one, the output would be the spike and the nominal signal. So the nominal signal is called LFP. Later we'll explain it. And this one is the trigger. So the upper one, sending trigger, sending stimulation, and get different signals. Okay, I hope you can understand. Okay, so the setup is like this. Okay, we back to this slide. In the structure of this research, we mentioned about the development of the bidirectional probe. There are many things, as you have seen in the previous few pages. And the next thing in the mice side, we will see it's a so-called hypersynchronicity as previously described, and we will also see its immuno characters like a conventional medical science, and also we get the many signals, and so do many post process for the signals. So that's the structure of the research. Okay, so just like the setup in the whole experiment, they were using 30 mice, 15 for wild type, and the 15, the other 15 is called APP-PS1. It's another model for AD, for Alzheimer's disease. Yeah. And in stimulation, there's a protocol. Protocol means there's like a standard. Every mice, every test, they follow the same way. So the protocol is composed of 6 sections with the intensity increase. So you can see in the first section, first 400 seconds, it's 100 microamp. And the consecutive 2 are 200 microamp, and then followed by 300 microamp. So this protocol was set because it's easiest to get a reproductive signal, and every time we'll get a response. So finally, the research team uses a protocol, and between different 400 section, they will rest for more than 5 minutes. Okay, in the paper as described, they do this experiment, do simulation consecutively 7 days, and every day they carry on this simulation in the afternoon. Don't know why. Maybe not afternoon. It's a timing for mice to wake up. Okay, then we see this curve again. The blue one is PBS, means no special ingredient, just a salt. But for the red one is for dopamine. Yeah, this curve is material dependent. Okay, I should say solution ingredient dependent. So for different material, for different ingredient, dopamine and other acid, the curve will be different. So in red one is for dopamine. The area for dopamine will be calibrated. Yeah, before they really do the experiment, the process called the calibration may make it the best region to test. It's in this yellow area. Okay, so this area is from 0 to 0.36, and they will feed this area into a 0.01 microamp and to 80 microamp. They will feed the 2 curves. Yeah, in the process of the fitting, means they need to find the right position for future test. Then we can see this plot by time. Okay, the horizontal axis is time. Time is positively to the cyclic voltage change, and the vertical axis is current. So as time going in certain time, the concentration of dopamine will be detected. Okay, so if in the previous description about the electronics and the material process, if you cannot fully catch it, there will be no problem. You just remember time and concentration will be correlated. That's the way we test the concentration of dopamine. And okay, this is called curve fitting. There is some mathematical ways to fit the curve. In that case, in future test, we can get fully scales numerical data. That's for the purpose. Yeah, the lower right plot is a smaller plot in previous photo. They finally come out with a curve like this. Of course, we see it, but for engineers, they like to describe it in a mathematical way, several equations. And before they really used it in detection, there is another way need to be done. You need to make sure there will be a few interference will affect this experiment. So use several interference like uric acid, lactic acid, and ascorbic acid, and 5-HT. So several ingredients mixed together. They try to test if there's any unwanted ingredient during the experiment, will it impact the result of the experiment. Unfortunately, in the right plot, you can see that dopamine is still the most significant responding, and for others, almost almost can be ignored, and only ascorbic a little bit, but not significant. So means this probe is usable and the collaboration procedure is correct. Then this is a real case. If the dopamine, we trigger it, once the stimulation was sent into the hippocampus of mice, the detected dopamine concentration is just like this, up and down, very, very fluctuation. And this one is no matter how strong, what intensity the stimulation is, the dopamine will increase, but in different manner. So there are many ways to estimate the response of this dopamine. This one is for concentration valley. They want to know the dopamine is gradually increase or stay or gradually lower. And a very important parameter is the spike varying rate. I suggest we first see this plot. This plot, I think, is very impressive. And if you see this page, I think this page is the greatest breakthrough in this paper. Please note this timing. It's from 3600 to 4000. And the dopamine concentration slightly lower down. And this spike means it's a sunburst. Even concentration lower a little bit, the spike increase dramatically, hugely. So what does it mean in real case? If a psychic therapist or counselor sees this plot and fully understand it, I think some counseling problem can be rethink about. Yeah, because in psychic therapists, they face a problem. Some patients, their emotion changes significantly after a period of calm, a period of so-called plateau period. and they may change their emotion fast. I think it is caused by this spike. And back to this page 29, it's in the beginning time. It's only to 1400 seconds. So in other research, I have searched some paper. I never seen such a plot like a very accurate time point that can tell the concentration and the spike. Because inside of a brain, if there any spike, of course, it's maybe cause some emotion change. Maybe this we can get comment from you if from neuroscience viewpoint. And the lowest signal is a LFP. It's a local field potential. Of course, there are still many signals on it. Okay. And for these few these few figures, the research try to characterize the behavior of the signal from the electrophysiological. But I should say this one in pre-electrostimulation has a highest firing rate and then gradually decrease. But this test, we can see that no significance there. It means maybe in later section of the experiment, the mice brain go into a paralysis state, and the spike amplitude seems no significant change. Okay, the average firing rate decrease. I think this is a different meaning because in 300 microamp, it's in the like a 4, 5, 6 section. It means when this section started, the mice has been experienced at least 100 microamp and 200 microamp. The response, the reaction has been lowered down. Okay, this interspike interval in rising period like this, it's relatively low. Then after the electronic analysis, we come to some spatial cognition test. That's we familiar in medical science. They use different group, as I have said, wild type mice and the APP-PS1 mice. Okay, the way they in testing this is to put the mice in the center of the Y maze, and if the mice go into A, B, C sequentially once, it is counted as one succeed. And if the mice go into the branch 25%, it is deemed to go into the mice the arm. Then the result indicates that after stimulation, the spontaneous alteration increased from 47 to 61. Means the mice was more active, more aggressive after the stimulation. But for decision delay, almost the same, 21% to 20. And after that, the mice brain were taken and slicing, do some immunohistochemistry. In this plot, we can see the left one is the pre-stimulation, and then after stimulation, post-stimulation. Some brown points are plaque. By visualization, we can see it's decreased as the same same bigger but different staining. Okay, this one is immunofluorescence. It's clear. If you see the middle one, the red staining point are plaque, Alzheimer plaque. And so before stimulation and the post stimulation, we can easily see the red part has decreased. And for wild type, we will see no red, almost no red. Yeah, so it means that it looks like effect. And the statistic numerically support our visualization. The mice brain after stimulation become better. This one is the okay. This one is the plaque number, and this is intensity of staining. Yeah, look like the post electrical stimulation mice brain has really reduced the Alzheimer's plaque. But for wild mice, they still keep the same. No plaque found. And further, if we do more magnification, we can see the dendritic structure. The lower photo, you can see this. Yeah, the same. The left one is for pre-stimulation and after stimulation, and this one for wild type. Okay, then analyze the cytoskeleton. We can see after stimulation, the skeleton exhibit increased, and of course for wild type, it's diversified. The shape and the number are the most diversified. And this is the statistic. We can see the number of branches and the length of the branches. After stimulation has a better performance, and the end point, of course, still significantly improved after the stimulation. Okay, so here now we look back about the hypothesis. First, we see the synchronicity has been observed, as I have described, and the behavioral cognition, spatial cognition was improved, and some immuno ways, the Alzheimer's disease has been improved. So we can conclude the experiment, the device succeed. But there's still some critique, because I think the intensity be used in stimulation is too strong, because 300 microamp, almost 0.3 milliamp, it's very similar to regular TENS. So if the stimulation is directly injected to the mice brain, I think it's a little bit too strong. So many information was lost. So it's a pity, but it also understandable, because in this experiment, the researcher hope to ensure their signal acquiring is constantly and reproducible. So they prefer to use a stronger intensity, but in the future, maybe we can get more information. If the firing pattern and dopamine or other endocrine secretion can be properly correlate, I think there will be a huge progress in neuroscience. We can expect for this day. So summary, the correlation between hippocampus stimulation, dopamine secretion, and the firing is validated. And the device, so-called bidirectional probing, like a neural revive flagship, successfully developed. Their invest is a success. And the electrophysiological and the electrochemical signal can be put in timeline. I think it's very helpful. We can more accurately estimate the right time to apply our therapeutic strategy. Okay, so the third point, just like I have said, it's very beneficial to our future therapy, not only in also in. So this is the presentation I have this morning. We have some time. We see appendix. There are many papers, but in different levels journal. So means many people are doing in this field. I think we can pay more attention on this. Okay, that's my presentation. Thank you. I hope you can have more comment for me.
Okay. Hi, thank you for your presentation. Is there any question from student?
好，谢谢你的演讲。那我这边就问2个问题。那首先是跟背景有关的。那我想请问，就是这篇 paper 看起来就是使用了一个他们设计了一个神经晶片，然后把它植入到小鼠的马脑回里面进行电刺激。那他选择了一个40赫兹的强度频率。那我想好奇的是，为什么是40赫兹这个特殊的一个频率？那第2个问题是，因为我中间电生理的图我真的都看不懂，所以我只能选择我看得懂的来问。那可能就是那个麦克格利亚他某发的聚会，因为他们所谓的这个40赫兹刺激后，induce 了大脑多巴胺的分泌，然后来让它这个貌似这个麦克格利亚的某发的聚会出现一些变化，然后导致它那个 A 贝塔的一些沉淀被代谢掉。那我好奇的是，他有没有去做过像是把多巴胺的某个receptor 给关掉，然后看看它这个某发的聚会不会一直被抑制住，来证明它们的直接关联性。然后看看这些淀粉酶有没有那个的代谢掉，有没有也被抑制住，来证明它们是直接关联性的。
这个我觉得非常有趣的，就是说第一个问题啊，40赫兹为什么是会被用来在这个处理上？其实这件事情啊，也到目前为止，应该它真正的机制还没有被大家所熟悉，不管是在物理学或生命科学或者医学上的研究，其实目前是不知道的，它是一个测试的结果。这个有待我们去努力。那么我这边刚在 Appendix 1这边有写到说，有蛮多的 paper， 而且从很高的 impact factor 到比较普通的都在研究。那其实这个是一个大家测试的结果。那我在去年1年前我有 present 的另外一篇是40 Hertz。那他那个时候是比这篇更为离奇，因为他用的是一个很弱的，几乎是一个 disturbance 声光刺激，那他用一个比较 visualize 的方法，看到了脑中的这种所谓 brain waste 被排除的过程。所以这个过程，他同时在我刚讲前述的论文里面，他也去做，比方说他同一个测试，他会用8赫兹、40赫兹、80赫兹同样去做。就是说可能您另外一个算是比较附属的问题，就是说，那我是不是随便拿个电去刺激都可以？那结果发现好像不是，就40赫兹它就有一个比较奇特的用途。所以这个我想是目前大家期待去解决、去解开的这个谜。然后你讲的第2个问题说关掉多巴胺的 receptor， 我觉得这个是我从来没想过的。我觉得您的这个想法是一个相当有 novelty 的想法。不过我这边有一个page 就是我这边 OK， 我有稍微加几页那这个就是整理出来目前在40赫兹上面有几个类别的 paper。那么您可以看最下面，就是我用粉红色圈起来的。 好，他就说目前的 hypothesis 是说，似乎有一种神经的 group resonance， 好，集体共振，哦，因为确实啊，在你看这里面，它除了电刺激之外，它有的用光刺激，有的用声刺激，哦，甚至我自己想要用那个一些场啊，就小局部的环境场去刺激，那似乎在生物体里面或者说人体里面，对这个40赫兹有一种特殊的接收器。但是不是多巴胺接收器？如果以目前的 paper 看起来，有可以分这几大类，而且都 effective 的话，那我觉得它的应该是不只是靠多巴胺的 receptor， 它应该是有很多机制在一起。对，所以这不过当然，因为您讲的这个方法也没有 evidence 啊，只能说是我提一些佐证，来猜想你的问题。OK， 希望那样回答到你。
可以吗？喂，谢谢你的演讲。然后我有个比较基本的问题，就我刚刚快速查了一下，发现这一篇在讲的amyloid beta 42，它是一个比较疾病早期会形成促进斑块形成的 protein， 但大部分我感觉大家在讲阿兹海默症比较会提到很有名的 protein 是超 protein， 那它也跟疾病进展后续的严重度有很大的关联。那为什么这一篇要选那个42而不是超？然后它后面也没有再去探讨。就是下游这些比较关键的 protein 对于疾病的影响，对，
是非常的 practical、非常务实的问题哈。那我觉得 A-beta-42 可能因为它形成斑块比较容易观察吧，这是我第一个。然后再来就是说这篇 paper，如果光是看它的在后续的数据分析上哈，我觉得它有做一些，但是似乎就是如您所讲，有很多东西还没做出来，还没做完。那但是我们反过来想，为什么这样的 paper 它会 Nature Communication 会接受它？好，它真正的 breakthrough 其实是在它的那个 probe。好，我必须讲，其实它这篇比较像是一个那个装置的 paper。好，但是不只是这样了，我觉得它这个图还是给了我就我刚刚讲的啊，就是这个图然给了我一些够好的这个 enlightenment， 就是一个启发。好，所以我觉得说，您讲的这个问题后续是不是能做，那肯定是在值得做下去。但是我觉得以它这样来讲，等于说这个装置初试提升，它就能够有这样的效果。我觉得它这个 paper 我还是很欣赏它的。那再更进一步，我也可以给您看一个图哈，就是我去年。好，就是这个图的右下图哈，这是我去年的 present 的一个 paper。好，那我那个 video 可以放到 YouTube 上，你有兴趣的话，我可以 share 出来，你可以去看。好，那他这篇 paper 他就是讲到，他用40赫兹用非接触式的方法去让他的 brain waste 的排除。那我想可想而知啊，不管你是套蛋白还是在比较初期的 beta-42。能够把脑中的废物排出，基本上这应该都会有好处。好啊，那这个是一个算之前的 paper， 好，2024年的 paper， 它等于用一个间接的方法回答到您这个问题。对，所以我也建议您也可以参考一下啊，我会把那个连结放到 IMTMU 上面。好，谢谢。
So let's have the last question.
如果说你要为这一篇下一个 conclusion 的话，你会下一个什么 conclusion？我会这样问，是因为其实我刚好稍微查一下，40 Hertz 有一些很棒的 paper， 也有它也是说在很好期刊，它的 conclusion 是40 Hertz 对于 Alzheimer disease 没有任何帮助。就是说，我觉得我不知道你有没有查询其他 paper 过，因为好像这是因为我不是这领域的啦，然后我觉得好像似乎这40 Hertz 好像有很 diverse 的一个研究结果，我不知道你是怎么看待的，因为Alzheimer disease 我觉得有很多一些相关性的因素啦，比如说类似说口腔菌相或者是说肠胃道菌相，我们可以说有些口腔的菌虫或肠胃道菌虫跟Alzheimer disease 似乎有一些关联性，但是我好像没有办法得到一个 conclusion 说，比如说特定的细菌会导致或者是 影响到 Alzheimer disease。我不知道你是怎么认定这个40 Hz 的，谢谢。
问题啊，我觉得这个是一个我们在思考问题必须要去想到的。好，那我个人如果先回答你刚刚问的第一句话，就是我如果要为这个论文做一个 conclusion， 好，我到底要怎么想啊？其实我的真正的想法是说，因为我们现在的医学大部分都是 chemical oriented 的，大家只认 chemical， 这当然有一个医学发展的过程，但是还有很大的区块啊，就是电波跟光子。好，这个是在我们常规的医学里一直被忽略的。那我认为这个40赫兹它就是等于是一个开端。好，因为我稍微讲一下，大概在2010年开始哈，就陆续有一些论文出来，它就是叫做 ELF Extremely Low Frequency。好，它讲到大概在数十赫兹，大概到300赫兹左右，对人体或者动物体、生物体有特殊的影响。那后来大家逐步标定这40，因为它的就是某一些比较正面的 paper， 它看出来是比较 significant 所以我想您讲的确实没错，有一些他觉得没有结果，我们也认同他，他可能有他的观点但是我还是觉得这篇 paper 对我最大，或者说这2篇 paper 对我最大的影响就是它是一个 encouragement， 是一个很好的鼓励，就是说人体的感应不只是对现有的化学，好，那我们的医学也应该可以把它 expand， 把它扩展到能够良好的运用电波还有光波这些方法。这是我回答您的问题。那至于说有些不同的观点，我想可能需要多一点激荡吧，因为您如果去查那个40赫兹的论文可能比较多了。我的印象大概2019年开始陆陆续续。好，那以我进医科所这2年来，确实我发现它的数量有变多。好，因为在我的第1年里面，我确实是常常找不到 paper 来 present。因为我觉得，我希望是做一些跟我过去光电还有电波比较有关的研究。好，所以这个回答你的问题。刚刚那边好像有个同学有问题是吧
？Because of time,
Okay.
let's invite Professor Shen Xunyu to give some comment.
好，谢谢啊。那个军良的报告，我有一些建议。对，容我先讲。军良的报告，我有一些建议哦。就是我觉得你已经是2年级的学生，那我知道你在职场上工作一段时间，但是你愿意再花时间回学校，就是想要学习你需要学或者感兴趣或者不懂的部分。所以我觉得这些建议你可能听了未必能够采纳，但是我还是从这个报告的本质的结构的问题开始谈。首先，这个 presentation 已经报第4次了，这个结构是不太正确的。从你快速go through你的一次 slide 啊，比如说你的这个假说不是假说，你的假说是 aims。What is the hypothesis？ 其实这篇 paper 它就是要讲这个 A 加 B 会不会更好 ，A 加 B 2种治疗方式会不会让阿兹海默的治疗有进步，所以它的设定就是他认为它会进步。所以这个假说不会是这样1、2、3、4，你仔细回去看，它是 aims。我设定这个假说之后，我需要去证明哪些关键性的问题可以 support 这个假说。所以我觉得你对于假说的了解，或者是还是有不太正确的地方。然后你的 summary 的句子非常整张 slide 非常 wordy， 请你直接到 summary 那张 slide。summary 非常的 wordy， 而且你仔细去看这些 summary 真的是这篇 paper 的重要的 finding 吗？甚至你还写出对，这个 successfully develop， 其实它就是第一件事，它证明说 A 加 B 确实有比较好，你应该写出这样的 sentence， 而不是你看，甚至你还 however all the progress 啊，这个不叫 summary， 是很简单利落的直数据告诉我第一个实验第一个大的 section 证明了什么，第二个 section 证明什么，这叫做 summary。所以我觉得像这个部分你也要再去厘清哦，因为这些问题在你的 final defense 还是会出现。如果你继续维持这种样态的报告的方式，那你没有结论。所以刚才同学问你说，你如果可以给他下一个简单的结论是什么？你的 slide 根本没有 conclusion， 也没有 discussion， 所以同学问你说，有不同的想法，有不同的做法，结论是没有效啊。所以你看 discussion 的部分就要把过去你的异同、支持这个 paper 的不认同的拿出来。 所以第一件事先讲这篇 paper 的结论，然后其他人的结论 support 或 against 拿出来，然后讨论，这叫做讨论。然后你可以讲出你的看法见解啊，为什么他们会有这种不同的？所以这个部分都 missing 在你的 presentation 里面，这已经是第4次报告，所以我比较惊讶的是这样。那再来你的回答问题的甚至你还有 appendix 这个附件啊。这个附件的方式，我没有在人家的这种 oral presentation 里面看过这种方式。怎么附件呢？你可以 show the core reference 在你的 background introduction， 这个是从引经据典从哪里来，但是不会在 presentation 最后 show 一个 appendix。这个我觉得你可能要再回去 check 其他人，参考一下别的同学比较好的报告方式。再来，你看回答问题的方式，我觉得这部分也要再做一些精进。比如说刚才同学问你说，那你可不可以给我下一个结论，简单的结论？其实你绕了圈圈，绕了一大圈，你有给他答案吗？我刚才问这个同学，其实他没有得到答案，但是你讲了很多很多，其实你没有办法聚焦在 Q&A， 就是很 clear cut 去 answer 别人的 question， 然后你给我们一个 long story， 最后还是没有回答到听众，然后就结束了。所以我觉得这件事结构上的问题这个是我比较担心的，因为你的一个博士的训练，我觉得这很 basic。那未来你在不管是 qualify exam 或者是 final defense， 你会面临同样的问题。如果这个结构性的问题还是不能做一个好正确的 presentation， 我觉得这是我们比较关切的。再来呢，背景介绍不足。你回到你的 background introduction， 请你回到前面的 slide。你的 background introduction， 你看看这个题目，你要告诉我们什么？如果你从你的标题数字 enter 会直接到那张 slide。你如果回到 title page 好，对不起 ，title page 看这个 title page， 你觉得看这 title page 什么是 keyword？title page 是第一页，什么是 keyword？ 你要让听众听得懂这种题目，什么是关键性的这个 term 一定要解释的，背景介绍一定要讲出来，我们才听得懂。然后看完这个，什么是你的关键字？你一定要在背景介绍。那你有没有做这个介绍？这是我在提醒你，背景介绍不足。我们顺的看标题完，下一章你讲了什么是 Alzheimer disease hippocampus， 对，然后再来你就开始讲到40个赫兹。说句老实话，到底现在 Alzheimer 的治疗的这个 niche 或者是需求或者是 gap 是什么？其实我都还没有听到。然后你就开始讲40赫兹有什么可以 enter information， 就像所以为什么同学不大知道为什么你锁定40赫兹？其实40赫兹的治疗过去在用在抗发炎等等等等，所以这个 core 的 reference 是告诉我们他发现了什么。你要锁定电生理的部分，你要给我们充足的知识，然后再来。第3章 slide 完，第4章已经是 rationale。rationale 我们过去是在告诉你 ，rationale 是整理你的 background introduction， 你讲了很多背景介绍，可是我们可能不是很熟悉，你在帮听众再整理一下刚才已经讲过的东西，并且 rationale 整理完，下一章就是 hypothesis， 基于 A、B、C、D， 所以作者提出一个大胆的假说。可是呢，你整理完之后，其实又回到这个实验的设计，往下第5。其实这里是很困惑，你要讲这篇实验怎么做的，实验的什么设计吗？再来又出现假说，第6章又是假说，有没有发现混乱？报告不是很 organized， 没有一个层次。再来假说完，又开始介绍这个 chip。再来，其实从刚才从第7章已经是他第一个 figure。这个实验的第一个 figure， 可是到这里继续往下走，其实你看看，你继续往下走，到后面甚至还有比如说你到16章，你说你想要介绍第16章 slide， 你想要讲这个 structure of this research， 到第16章其实已经讲了好几张 data 了，怎么还会是 structure of this research？ 所以标题显然的 subtitle 显然是不正确的。然后呢，你仔细回去看这篇 paper， 这篇 paper 最大的 contribution 是什么？其实应该是说这个 dopamine 大家都知道dopamine 是一个很关键问题，虽然也有人讲alpha 这个 tau 等等，但是目前的治疗方式，第一个没有办法精准的刺激大脑的深层位置，第二件事情没有办法控制 dopamine 那些量，它的表现的情况。所以这篇 paper 它的 value 是说，他发现用这种无创的这种 chips。它可以精准的 sensing， 而且 control， 所以这是他这篇 paper， 其实他觉得他可以发表在这么好的 paper 的最主要。可是你在报告的时候，其实没有办法去呈现这部分，然后在讲电生理部分，也没有让你的听众能够 带着我们读这个图，可能是变成一个人的武林。这个图可能只有你看得懂，可是我们都不做电生理的，我们纵轴、横轴是什么？图怎么看？我们都不能理解。你只能告诉我说啊，这篇哦就是这样增加减少。所以这是我给你报告的建议，因为我觉得在你 Q1 跟 Final Defense 上都会遇到同样的困扰。然后你的报告这4次以来，我听起来其实都有类似的问题，所以我今天给你比较多的这个建议哦，你可能听了觉得不是很舒服。但是这些部分你还是必须要去 modify， 否则我相信你下次 presentation 还是犯同样的问题。
其实我非常高兴啊，因为您能够给我这么多的指导。那么我自己
先暂停哦，因为你的时间已经结束，老师时间我要赶快收尾了，不好意思。
So let's invite Professor Xu Zhenrong to give some comment.
我想能够接受这么多老师跟同学的建议，这非常非常的重要，因为这个是一个seminar， 不是一个科普的报告，所以它一定有一个很严谨的逻辑的架构。那因为你也可以参考这个期刊它的整个撰写的布局，那这个可能会比较有系统化的来介绍这个主题，比较不会这种跳跃性，因为到后面可能都会跟不上这个具体的这些逻辑的关联性。那另外就是在有些图的解释上，比方说像在它有做几个不同的 ES 的刺激之间，中间还有一个 concentration 的这个形成。那在你的论文里面可能没有介绍到，它为什么还会有一个额外的 concentration 的一个讯号的一个增长。那这个地方可能是在理解这个物理刺激结合这种生理学现象的时候，可能都还需要去理解的，怎么去解释清楚。那我想这个，因为我也是第一次听这个40赫兹在 ES 的刺激。那我想lab 里面我们有做一些不同的光的调控。那我想这可能有很多的物理性的。那光的调控它并不是用频率，它是用这个波长来控制这个 mitochondria 的呼吸传递链的第4个复合物，所以它可能不同的刺激有没有效，可能它取决它是不是有一个特定的这个 receptor。我想这个解释才会比较能够周延，不是说40赫兹的光或是电讯号一定都是会有相同的效应，取决它是不是有对的这个 receptor。然后以上的建议。
我想因为时间关系了哈，我想曾老师的建议，我想是非常具有那个参考性，就是说，就像我们在写计划，你的 hypothesis、rationality， 你的 M， 事实上是有要求的格式啊。好，尤其你 conclusion， 其实有时候 conclusion 最重要。其实我有发现，你不要把它自己整个抄下来，你要把它变成你的图，而且最好是自己画个卡通图，就把它要做一个 conclusion。那有时候我们一看就清楚，有时候看 paper 看规模看不，事实上直接看conclusion 的图，你大概就了解。好，我想大概陈老师听过好几次了，我是第一次听了，也是现在第一次听啊。那我也是给所有的学生建议，以后不要找中国的期刊。其实我常讲 ，I don't believe from the paper from the China。而且事实上你看哈，很多东西 error bar 其实非常 closely。事实上你看很多那个 p value 不是很 dramatic 的一个 increase 或 decrease， 也就是说在那个地方有操作的空间，所以我很讨厌。我不是讨厌中国人，我是很讨厌中国的期刊。上次之前有人讲过，你看 almost 80% 都是，我敢这么讲，所以我常常跟学生讲，不要 seminar， 不要去 paper 这么多，不要去读中国的期刊，因为中国的期刊已经把学术完全扭曲掉了。好，只是当然我们现在我不是你的错，我只是说建议所有的学生，以后我不想听到中国的期刊，这一点我是很insist的，很坚持。啊，期刊这么多，为什么一定要去找中国的？因为中国的社会对期刊已经完全学术完全扭曲掉，他们为了 paper 发表不择手段了。你不要以为他是 key 美国的重点实验室啊，对不对？而且我看到，对啦，其实有时候，但我们不针对里面，我们也没有 evidence， 只是说尽量不要去用 paper 这么多。我是强调这句话 ，paper 这么多不用去选中国的期刊，这是我的要求。那回到结果我就不讲了。那刚刚有同学在问了，其实都问了很大的问题。我跟你讲，事实上现在只有像林信荣花莲慈济医院的林信荣，事实上他做Alzheimer做直接，他们也做了很多，但是到后来都失败。最重要是什么？就像你现在做的一个 chip 放进去， how long stay？ 这个它的电量能够持续多久？现在这是所面临到的问题。整个理论可能我可以让我接受40赫兹，我也可以接受，但是对治疗来讲，如何去治疗，如何去 sustain， 它的 device 如何去置入完以后，因为它是开脑要置入到 hippocampal， 他说他可以他有放电池可以撑很久，你能撑多久？那你撑完以后，这个界面是不是还要再拿出来，还要再开一次脑？所以有时候说这个东西，为什么到事实上在做这个，事实上它不是主流。对 Alzheimer 还是要回到药物。那刚刚有学员讲到 top protein， 是我跟你讲，也有人认为 amyloid beta 是假的啊，是不是有人说被骗了40年？因为我应该也看到过 amyloid beta 事实上跟 Alzheimer 一点关系都没有。他说 top protein 也是啊，所以那你就说 amyloid beta， 你可能不知道，40在 brain， 血液中最多的也是 amyloid beta， 它是40，在哪里？血小板。所以也就是说，事实上整个 Alzheimer 是 overall 一个全身性的反应所造成的。所以为什么到现在没有药医？我们在药理学上就给 L-dopa 之后那变成 dopamine， 那再可能给一些 cholinergic， 就是副交感神经药物去刺激它的那个它的整个中枢的那个的 sensitivity 啦，因为都是增加，也是一样增加一些交感神经、副交感神经的活性。所以也就是说，到目前为止，就是说陈立告呀，声光也可以啊，什么都可以，这也是事情。但是这种物理性的最大的问题就是如何让病人 sustain， 对不对？你即便放进去啊，总会没电吧？对不对？啊，你总不能 brain 那边拉又不是老鼠，人又不是老鼠，还可以拉一个电线，说我给它外面刺激，人是不行的。所以也就是说，这些发展是有它的 limitation 的。那因为夏同学他的背景是生医工程的，所以他来找我的时候，其实我也有点困难，有点慢。但是他跟我讲说，他跟杨老师在合作，那我就放心了，因为市场我也不是很懂。那我也借着我也真的很希望借着夏同学可以跟杨老师的实验室，因为杨老师在医工学院他做得非常好，也是做一些 connection， 所以那天我也鼓励他了，说是啊，我虽然是外行的，但我也期待你能好好去做一篇真的有贡献，而且好好的跟杨老师学习。你好跟坏，跟我没关系，跟杨老师开玩笑。好，这大概就这样啊。
Okay, so that's the first seminar. So let's take a 3 minutes break.